Welcome everyone to the Leader webinar, IP 101 for the Operator and Engineer, Part 3, IP Jitter and Timing. Our hosts today are Steve Holmes and Kevin Salvidge of Leader Electronics. I'm Kristen Berkery, and I invite you to send me your questions in the chat, and I'll share them with our presenters today. And now, I'll welcome Steve Holmes.
Thank you, Kristen. I want to welcome everybody here today to our Part 3, looking at packet jitter, timing, and buffers. So today, we'll be going through this, and as Kristen said, if you've got questions, please put them into the chat window, and we'll review all the questions at the end of our seminar. And we also have our distinguished guest, Kevin Salvidge from our Europe division with us today. Hello, Kevin.
Hello there, Steve, and thank you for inviting us to join you today.
You're most certainly welcome, sir. So let's kick this off and get going. So in today's webinar, as we've indicated, we're going to be looking at packet jitter, timing, and buffers. And what does packet jitter exist, and what causes it, and looking at inter-packet gaps and what this means, and how this all comes about, and when it's in trouble and when it's not in trouble. We're also going to look at different sender models, because as 2110 has progressed, we've come up with different types of transmitters that are sending the data and different ways they're doing these things. And just as we came up with ion jitter for looking at SDI, we've come up with buffer models for the IP, looking at how transmitters are behaving themselves and what's going on with that. And then always people are asking about, well, what about timing a 2110 system? Where is it relative to black burst or tri-level? And looking at PTP versus RTP. So we're going to delve into all of these different things. We are going to be having some upcoming webinars, and one of them we'll be looking at another round of PTP and looking at what's coming up with PTP and some new pieces that have been added to PTP. We're also going to look at 2022-7 protection switching, the one-for-one packet selection. And as we go on, we will come up with more and more seminars. A lot of these are based on your feedback of things you guys want to hear about. One of the things you need to remember about IP is it's just another I/O interface. It's just another way to get video, audio, and data to or from a switch, just as we do with a router or a switch in SDI today. It's just on a different transport medium. It's doing the same exact job. So in SDI, we look at levels, we look at I, we look at jitter, we look at EAV, SAV placement, CRC errors, pathological issues, and the like. And as things go on here, IP is very similar, but in IP, we're going to look at packet jitter. We're going to look at sender models, which is part of the ion jitter part. Network buffers, that's more in time with looking at jitter in SDI and how decode buffers deal with all of this. So it's all the same types of things, it's just how we do this that has changed. Just for a very quick review, you've got to remember that in 2110, we're using essence payloads. So we've taken the conventional SDI and broken it down to its component parts. So we have 2110-20, which is our video layer. We have 2110-30, which is our audio layer. And then we have 2110-40, that is our metadata. So that's going to be things like time code, captions, AFD, all of this stuff that we normally used to put in the vertical interval. Each one of those will be an individual payload or an individual IP stream. So these 3 IP flows are going to make up our program. The other thing to remember is troubleshooting really has not changed. The I/O has changed, but how you start and what you do is still really the same. It's still a divide and conquer. You've got a network, you need to really know kind of from a block diagram perspective, what your network looks like. And it's still a divide and conquer. You jump into the middle and you look, is it this way or is my problem this way? And that divides your network in half and cuts half of your work down and allows you just to get onto the piece that's actually giving you problems. The other thing is our 2110 networks are getting more and more complicated. They're coming from more and more places. In some cases, we've got individual video and individual audios that are coming into some form of aggregation switch. Off of that aggregation switch, they're coming out to some type of distribution switch and flowing into the main part of the network. So it may be a switcher that has the video flows and the audio flows going into it, combines those together and gives us our output. Or think about remote operations where you've got live events. In most cases, live events, we've got a video feed and we're switching many different video feeds, and someone's doing a voiceover on top of those video feeds, and the switcher is going to put those together and send those out. We're going to send those to wherever our network operation center is, into maybe a leaf spine architecture, and put that out on our network. So there are many different configurations, just like there is in SDI when we look at this stuff. So we have the ability to have our waveform monitors be able to actually look at SDI and look at IP and go to the different points within the system. We could have our LV5600, our leader LV5600, looking at the source, looking at different points within the network. We may have a Salvidge QX that is in the middle and looking at different points. And then we've got the SX tag, which is a very valuable tool because it's portable and you can get behind the rack and you can move around very easily and quickly. So it's just the tools that we're going to use that are getting into this. So we can have the waveform monitor do an IGMP join, or we can actually go and have NMOS, go to a network control panel and pick source, destination, hit take. That connects to an NMOS system. The NMOS system will then route the video, tell the receiver what the video is, and set the entire system up for you. So let's get into today's meat here. Looking at packet jitter, spacing, and cinder models. So one of the unique things about the IP network is that the data rate is going to be coming out at somewhere right around about 1.3 gigabits for a 1080i output. But the line rate of the data is going to be moving at either 10 gigabits or at 25 gigabits. So the pipe is not going to be 100% full coming out of the transmitter. We're going to have spaces between each one of the IP packets. So we're going to fill up an IP packet. We're going to ship it at line rate. We're going to fill up the next IP packet, ship it at line rate, fill up the next IP packet, ship it at line rate. So you're going to get out of the transmitter a nice, smooth, clean flow. But once it hits a switch, what the switch is actually doing is it's a statistical multiplexer. It is getting many feeds from different ports and aggregating those feeds together and putting them out on another IP leg. But in a lot of cases, you're going to have two packets show up at the same time. One packet's got to get in front of another packet's got to get behind another packet. There's also now going to be PTP introduced into this. So it's going to move packets around. So you get a little bit of an accordion effect once you hit your switch. And it's looking at that output and knowing what that output looks like in your system to know when that output is running correctly versus when it starts getting stressed and starts running into problems. So here's actually a view of normal arrival time coming out. In this case, this is an LV5600, looking at an audio, video, and data flow as it's coming down the pipe. And what we're actually looking at here is the time between packets, how often the packets are coming, and how evenly spaced these particular packets are. You're gonna have a little bit of change here, as you can tell. On the left-hand side, we're looking at how many microseconds between packets. So we have packets coming moderately early and packets coming about 8.2 microseconds later. But it should be a nice, consistent, smooth flow. This is what you need to look at and learn what your system looks like so you know when this ends up getting in trouble. And as things get loaded, switches get stressed, people try to oversubscribe a port, put more data than the port can handle. This can start looking more ragged. So as I turned around and added more and more data to my little switch and started stressing my switch, you can see that the data started changing a lot between the minimums and maximums, and my average, which is that blue line in the middle, started jumping around all over the place. These are the things that you do not want to happen. So when we look at this and you look at it over time, you can see what these things look like, and you can see how your system's going to respond. So this is like looking at a transmitter with the jitter starting to look bad coming out of the transmitter. It's just going to get worse as you go through more and more and more network elements. So these are the things that you want to be able to know exactly what your system looks like when it's operating correctly and when your system is starting to get sick, and be able to look at these things.
Steve, I think you made a good point there that you need to look at this over a prolonged period of time, because typically with networks, they don't just change suddenly. It's normally a gradual change.
Yes, yes, unless someone has done something like oversubscribe a port or oversubscribe an encapsulator. I have seen that several times where people have got a encapsulator where they've got SDI feeds coming in, and it can take 6 HD flows, but all of a sudden they take one of the HD flows off and they put on a 3 gig flow, and now you're sending out more than 10 gigabits worth of data, and everybody that's on that encapsulator is now in trouble.
Yeah. So obviously the graphic you're showing here at the moment is from basically a 2-minute spread.
Yes.
But obviously I know on the 5600 you can go up to 72 hours. So you've got a real long window of monitoring.
Yes, and let's actually take a look at that. So here's actually a live system, and we are looking at my spread on this particular system here, and it's working very nicely. And as Kevin said, if we go into chart setup here, if I get the correct mouse, go into chart setup, we can look at from a 2-minute window out to 72 minutes. So we can go out 10 minutes worth of data. I can go out 30 minutes, an hour, and 2 hours. And there's where I turned on my system. This is something you wouldn't normally have in an operating system, but there's where I turned my system on this morning. So a little bit, just a touch over an hour ago is when I turned my system on. But what I want to get to is if I turn around and add some stress to a switch I have and add more data to it, you're going to start seeing things happen within my system here. And all of a sudden, things are taking off here. And you can see that I've started to stress my switch and things are starting to increase. So what I've done is I've really taken a very small little switch I have in my office and I've put a lot of data into the switch. I haven't changed how much data that I have coming to me. So if I go up and look, I still just have my one video flow, my one audio flow, my PTP coming to me. So I have not changed this, but I have changed what is going on in the overall nature of the switch. And you can definitely see that something has happened. And that's why I say you need to really get a good view of what is going on and how to look at this data over time and be able to know what your system at this point really should look like to be able to look at this. If we turn around and take a look at how Fabrics looks at this, since now Leader owns Fabrics, and we're representing both products here. Fabrics looks at this a little bit different, whereas Leader is looking at this as a time graph across the bottom and then looking at packet jitter going up on the vertical axis. When we look at the Fabrics, it's looking at the jitter across the bottom and how much jitter we have going across. It's the equivalent of taking the time chart and turning it on its side. And what we're actually getting here is over on the left-hand side is the main data. We happen to have the vertical interval gap since 2110 in most cases does not send, well, in all cases, does not send the vertical interval. You end up with the last packet of the field or the frame. You have the vertical interval, and then you have the first packet of the next field or frame, depending on, so in this case, it is interlaced because I have field 1 and field 2 here coming up. But if we turn around and zoom in, we can turn around and look at the main 2 spikes and see that it's almost a Gaussian shape of the data. Rather than going up the chart for jitter, it's going horizontally for jitter, so it's moving this way for more and more jitter. And as things get stressed, you can see it really widen out as things get stressed out more and more on this. So if we turn around and look at, just give me 2 seconds here. we turn around and look at the Salvidge QX. Up on the top up here is the jitter. And if I double click on it, we'll make it larger and put the scaling back to automatic so you can see the whole thing. So here's my main data where almost all the data is, the vertical interval, the start of field 1 and field 2. But really what I want to look at is these two little spikes, so I can zoom in on those two spikes and see what the distribution. I missed the first spike. Let me redo this. Get over to the left, go there. There we go. And zoom in on those two spikes. And so you can see the data that's coming in here and the distribution of that data over time, which should be a nice, fairly Gaussian, but a very narrow pulse. And again, as I add more data to my switch and turn around, you can actually see that expand where it starts almost looking like one big, huge blob that the data is really coming in early, really coming in really late. So early packets are on the far left, more and more time between packets is on the right. And you can get to a point where if you send packets too late, you are going to turn around and underflow a buffer. And if you send too many packets too early, you're going to overflow a buffer someplace within your network. So these are things you really need to be knowledgeable about and be able to look at them and take a quick look and say, nope, that looks normal, or nope, yep, I'm definitely in trouble here, and go back and look at what things are doing and how they are doing what they're doing. So the other piece here that we need to know about is, just like ion jitter looks at the output of a transmitter in SDI, the sender buffer modeling looks at how the performance is coming out of transmitters and whether or not I'm sending data right out of my transmitter that's already really jittery and going to give me problems right off the bat or not. Because we have different types of transmitters, we needed to come up with a solution to be able to monitor the outputs of these transmitters. We have the original designs that most people came up with, which is out of an FPGA, which puts out packets at a very, very nice, clean spacing. Then someone came up and said, well, what if we took that nice clean spacing and took that gap that was the vertical interval and just delay all the packets so it's a clean flow? And then we get into some of the newer servers where they just have a conventional NIC in that server and they're doing everything in software. And now the processing gets in the way of being able to put these packets out absolutely perfect. So they have come up with different timing models and different outputs for these things. The first one, which is probably the most popular and the most out there, is the narrow gap system. And that's what we were just looking at, to where we're going to send all of the data. We come up to the last packet right here, which is going to have my M bit in it, my marker bit, saying this is the last field or last frame. And then you're going to go through the vertical interval, and then you're going to start the next field again and continue on. The narrow linear is the other one I talked about, where we're going to take this and just spread it out ever so slightly so that we completely fill up that vertical interval gap. And this frame here that has my end bit is now over here right next to the start of the next frame. So now you get a smooth continuous flow at all times. The third transmitter is the wide transmitter, which is the software transmitter coming out of just a conventional NIC. So the processor itself gets in the way of putting this data out, and you get a lot more of an accordion effect looking at the data coming right out of the transmitter. And this really brought some new stuff up when they first started putting these out, because there was a lot of receivers that they'd take a software sender, plug it into their network, put it into a conventional receiver, and get absolutely nothing or get trash out of that particular receiver, because the data was varying so much they didn't have enough buffer in the receiver to be able to handle what was going on.
So Steve, do you see this as being one of our biggest challenges? Because the way technology evolves, people want to move from hardware to software, because obviously it gives them more power, more powerful processing, probably less power consumption. And, you know, are we going to see more and more devices that are wide senders out there in the market?
I believe you are absolutely correct. I think we are, because being software, it's much easier to just write the code, put it on a server, conventional server, and it's much more flexible than turn around and writing FPGA code, which is not as near as easy and a lot more expensive. So I think you're absolutely correct there, Kev.
So this is one of the real collision points, isn't it, from a traditional broadcast engineer who is used to SDI being synchronous, packets arriving at a regular interval, to an asynchronous world that data centers are used to. Yes.
And that widespread in those last two charts, when I looked at it on the Leader LV5600 and I looked at it on the Fabrics QX, where it was wide, that's what it looks like coming right out of a wide sender. It already looks like it's in trouble almost. So you have to have much wider buffers in your receivers to be able to handle that. So if you've got receivers that were made for either narrow linear or narrow gap systems, and someone puts a wide sender on there, you may have receiver issues, and you may not be able to decode the video correctly. So part of the reason we came up with these different types of buffer modeling. So the buffer modeling deals with looking at the data coming out of the sender. So over on the left-hand side over here, I've got my 2110-20, my video sender, and it's got a little bit of spacing between its packets, but they're moderately tight, so this would typically be a hardware sender. And it's going to turn around and send that data out, and we want to turn around and build a buffer that has a continuous smooth drain rate. That is going to be the IP line rate, and see how many packets do I need to buffer up so that I don't underflow or overflow when I turn around and put on a continuous drain on that leaky buffer. And in most cases, it's right around 4 packets is the norm for looking at a typical hardware sender coming out, and you should get a nice, smooth, continuous flow. So looking on the bottom right here, we've got the LV5600 looking at the video flow. And if I zoom in just a little bit, you can see that it's just over 3 packets. So it's right around 4 packets that it's taking to turn around and absolutely smooth this out. In the QX, it's looking at it virtually the same way and just looking at how many packets that it's taking to smooth this out. And this is the equivalent of the eye and jitter looking at a transmitter coming out of your system. The other thing that we need to concern ourselves with now is I'm going to have to take this line rate of either 10 gigabits or 25 gigabits of data, and I'm going to need to be able to put it out at basically the SDI rate, the actual raw rate, into some other processing gear that's going to eventually give me my picture. So we have the data coming out of a sender here, and it's coming out at 10 gig or 25 gig. It's going to go into a buffer, but now the output of that buffer, the leaky part of that buffer now, is going to be our 1.3 gigabits, if it's 1080i, going to whatever device. So we need to make sure that we aren't overflowing or underflowing that particular buffer. And this is where things get really different between hardware senders and software senders. And we know that as we increase buffer sizes, you're holding more data for a longer period of time, so you're actually introducing delay into your system. So for a hardware sender, we should be able to do this in 8 packets or less, which is approximately 2 lines of data in 422 1080i. So you're going to buffer roughly in IP about 2 lines of data in order to get the data back out at a nice smooth rate. But as soon as we go to a software sender, we're going to have to hold 720 packets in the buffer before we can put it out, because there's that much accordion effect of the space between packets and how many packets I'm getting crunched together, which is now about 20% of a frame at 422 1080i. So it really changes things that now you got a buffer of 720 packets when you probably built your original receive buffer probably right around 16 packets to make a nice round number for binary. And all of a sudden, someone comes in with a system that is going to require, 700 some packets, and it's just going to overflow the thing. So they've really had to change the buffer model. And in a lot of cases, systems now have, okay, I'm going to set up for a narrow or I'm going to set up for wide. Because if you always set up for wide, you'll always have that 20% frame delay coming into your system. But it's something that we need to look at to see what our decode or our rate conversion from line rate down to actual video rate is actually going to give us.
So Steve, a couple of people have kind of highlighted to me, you've got a camera at the front end, which is capturing a resolution and so many frames a second, and that's creating that data at a regular interval. Obviously, the display device has a nice steady flow. So what you've got to manage in between is, as you said, this buffering and concertinaing of the network, because the devices on either end are either generating it nice and smoothly or want to receive it nice and smoothly.
Yeah, if it's a camera, yes, cameras will normally put it out, the data absolutely pristine and nice and smooth. But if it's a server playing a file and it's a software server, that's where you get into that accordion effect of the output, because you're dealing with the OS getting into the middle of putting this stuff out. And it's in the middle of doing something, so it can't put data down to the output card. So you wait, it gets done with that, and now it puts several packets down. And now it waits and goes off and does another job. So that's the issue we've got going on with the looking at this stuff. So again, let's go jump over here. And we can go off of our packet flow screen and go over here to buffers. And so we can look at our CMAX, which is the 10 gig to 10 gig output, making sure that that's nice and meeting within that roughly 4 packets. So this is just coming over just a little bit. And the reason I'm coming over just a little bit is because I didn't want to reconfigure my system and go directly into my sender. I'm still coming through actually 2 switches here, which is not how you should measure this. You should have your system, just like SDI, should be a 1 meter coax going straight into your measuring device. Your measuring device should be plugged in straight to the transmitter in this case. But like SDI jitter, you do use it as a troubleshooting tool throughout your network. You can also use this as a troubleshooting tool throughout your network. It just doesn't mean you're going to necessarily meet the exact standard and exact specs, but you need to know exactly that it is not giving you really, really screwed up data. And then if I change over to my VRX, so now this is looking at going from line rate of either 10 gig or 25 gig down to my 1.3 gigabits. So if you look at the top of the screen up here, you can see that my data rate is 1.3 gigabits, which is what my video is when I remove the vertical interval and I remove the horizontal interval. My leftover actual raw video making the raster is 1.3 gigabits. And what does it take to get that from 10 gig down to 1.3 gig in this case? So I'm running 10 gigabits here in my office. And I get a nice, clean, smooth output in looking at this. If we turn around and look at how the average looks at this, rejoin this stream, it's going to turn around and generate a graph, and I can look at either the VRX. So here's the CMAX. And so this is looking at my output here from the 10 gig to 10 gig output, and just right under where I'm plugged in here for this particular measuring device, I'm getting just under or right at 3 packets, which is a beautiful output. Then if I change this over to look at the decode, I can turn around and look at the decode here. Reset. So now you'll see that it's coming in at right about where I'm at with this unit plugged in. It's ahead of the leader, so it's not going through as many switches. So it's looking at roughly about 5 packets for my decode buffer, going from 10 gig down to 1.3 gigabits. I'm having to buffer roughly 5 packets. So it's well within the 8 packet limit of what I have going on in this system. So both devices do the same exact measurements, just slightly different ways of doing things here and getting through this. So let's take a peek at timing. This is probably one of the biggest things, I don't know about you, Kevin, but that I get asked about is my 2110 in time with my Blackburst or tri-level that's running the rest of my facility? You get that quite a bit?
Yeah, because obviously a lot of people have implemented kind of IP proof of concepts that have then become established, gone live, and they're beautiful little IP islands. But then obviously you need to kind of go across into the SDI world. And I would say most of the converter products these days are very good.
Yes.
But what you've got is you jumping from one to another. And if your reference for black and burst and PTP is not coming out of the same device, you could be in for a world of pain.
Yes, because 2110 does mandate a synchronous system, that it is timed to PTP, which now if you're in a world where, yes, you've got some SDI, you've got some IP, and you're going back to SDI, those two worlds have to be in time with each other in order to make this whole thing work. And we do have the ability to be able to look at the timing and be able to look at things. But the thing you need to remember when we're looking at this is we are only sending this green portion over here, which is the actual video raster. That's why it went from 1.5 gigabits down to 1.3 gigabits. And we need to make sure that this point in time, the start of the frame in IP, is exactly the same point that it is in SDI, because you're still going to go into a switcher, you're still going to go into a router, and you still need to be able to switch and have things in the proper place. So if we look at the difference between the start of a frame and my active picture raster in 1080i, there's going to be a 21 line delay before I put out my video. And then there's also going to be about 4.1 microseconds of delay to account for the horizontal. And if you look at the chart here, this was dialed in, so this was absolutely perfect. In most cases, what you're going to see in this is a little bit of movement, just like we always have. So this is actually looking at my system that I have here in my office. Yes, it was 21 lines off, as it should be, 21 lines delayed, but the horizontal in this case was 10.15 microseconds. This is not uncommon to see the horizontal off just a little bit from the absolute perfect 4 microseconds in looking at this. But what you want to see is that this is absolutely stationary, absolutely still. So what this is looking at now is PTP, which starts at the same place that black burst starts or tri-level starts, to RTP, which is the timestamps of the IP packets that are making the picture. Those two should start, you send out PTP, it starts out at pixel 0, line 0, and the actual video data, which starts 21 lines later, but they should be absolutely stable and exactly the same time with each other and holding constant in going through all of this.
Steve, is it just worth reminding people, obviously what you're showing there is an interlaced measurement,
Yes.
but if you move to progressive, those numbers change again.
Yes, so this is 1080i, which is going to give you 21 lines. If I went 1080p, since I'm progressive, you're going to take that line count and double it. So it's going to be 42 lines later. And as you go up in data rates, it keeps increasing because the vertical interval gets larger in higher data rates. And we start talking 6 gig and 12 gig, they're even bigger. Thank you, Kevin. But if I look at the ratio of, down here in the bottom left-hand corner, you can see that this is now looking at where is PTP to black burst. Those are the ones also that you want to make sure that my reference for my system and my reference for the rest of the house that's black burst are perfectly in time with each other. And those should be 0 by 0. Those should be vertically 0, horizontally 0. And as we all know, The horizontal's always fractionally off. It's hard to get that piece down to absolutes, but this does meet the tolerances we have because I've got a nice green 0 in the center of my target here, looking at that my PTP is perfectly locked to my black burst, and those two are tracking each other absolutely perfectly. This one here now is looking at, okay, I've got PTP, it's locked. I'm looking at RTP. This is the one that's actually going to show you, and I'll show you in a minute, whether or not your video is locked or not.
And obviously, Steve, this is why you need a test and measurement device that can connect to both reference sources, because you need it in a single box. You can't do this across 2 different products.
No, there's no way. Absolutely no way. Yeah. And this is absolutely critical in your system, that your video be locked, your PTP be locked to the same as the rest of your house reference. And we can actually see right now that I am virtually exactly what I just saw, which was 21 lines out and 10.152 microseconds horizontally delayed, but they are absolutely perfectly still, which is telling me that my PTP and my video are absolutely locked to each other, and my video frame is staying exactly at the same place relative to RT, or rather to PTP. So my RTP timestamps, which are the timestamps of the IP packets in the start frame, is exactly where it should be. If I go in and change this to look at PTP to black burst, and there it is at 0 by virtually 0, and they are perfectly locked with each other. So my black burst to my PTP are absolutely locked. Now, once in a great while, you might get a very small horizontal movement in this. And that's just PTP recorrecting itself as life goes on. But normally you're going to see an absolute perfect 0 here. But if you look at the clock up in the H phase, you might see that change by a few microseconds once in a great while. Right there, it just changed and changed back. That is very common to see that small of change within what PTP is actually doing, accounting for the delays in going through the IP network. So it's having to deal with switches and switch delays, but going through all of it. The QX does this fractionally different, but the same exact readings. All it's looking at now is media latency. And so the media latency that it's looking at then should be that 21 lines. And if we go back here and look, so my total phase is 6.32 microseconds of total delay. And we look here, and if you look at 6.34 microseconds, just a small horizontal offset. So 6.34 microseconds is 21 lines out. So this is telling me that, yes, I am 21 lines out in looking at this information. But it's just giving you more measurement in a horizontal spread of here's 0 and here's where my first RTP packet's coming in, and it's exactly where it should be coming in. And then on the QX, we can look at external reference versus PTP, and this is where we should be 0 by 0. And I'm right on, no lines, and I'm off by 2 pixels. Woo-hoo. So it is perfectly locked also. Looking at this on the QX, two different timing models. My reference in this case was 525-5994, i.e. Blackburst, coming in for my lock to my QX that I have here. If we look at the timing, and I'll drop this guy down so we can see it kind of in the middle here. And we look at media latency. There, if you look at the mean, there's my 6.3 microseconds, my 21 lines. And if we look at where I am versus reference to PTP, and there I am, 0 lines and now 4 pixels off. And so virtually absolutely locked. It's not moving all over the place. It's sitting absolutely still. And we can look at this from several different perspectives here in looking at this.
I mean, the great thing with these tools, Steve, are for people who are familiar with them in the SDI world, it's the same graphical display.
Yes, yes.
There's nothing to be scared of here. This is it's giving you that information exactly the same format as you're used to in an SDI world.
Yes.
Obviously, the difference is we've now got a PTP reference, and obviously we've got RTP timestamps to bear in mind.
Yeah, instead of EAVs and SAVs, we've got RTP timestamps. Instead of Blackburst or tri-level, we've got PTP. Yes, exactly. Absolutely, Kevin. Here is what unlocked video would look like. So now my reference is PTP to RTP. And what's happening is the RTP timestamps, because they mark the beginning of a frame, and since the frame is moving around, those RTP timestamps are moving around. And you see what you would see if you were looking at Blackburst in unlocked video or looking at tri-level unlocked video. It's just swinging all over the place. And you'll see a line count that keeps changing. And the line count in this case just keeps counting down, counting down. It'll just eventually go all the way around in circles. So this is what actually unlocked video would actually look like when you're looking at this stuff. In the QX, we actually use the VRX buffer model. So when you're looking at the 10 gig to actual video rate decode model here and looking at that, you can actually see this thing is just constantly sliding and constantly sliding and constantly moving. So it comes up and shows it in just a fractionally different way of looking at all this data. It would be just taking the right mouse, putting this in VRX, and if the video becomes unlocked, you'd see that thing climbing. And there you see it. It just starts climbing, 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 rather than being a nice, clean, smooth flow. On the Leader LV5600, my PTP is still perfectly locked to Blackburst, but if I look at my RTP time, which is now looking at the timestamps in the video, you can see the video is just flying all over the place, showing you that same unlocked piece here. On the LV5600 or LV7600, the Leader, all of the IP measurements are done under the status button. So once you hit the status button, all of the measurements, and you're looking at an IP flow, all of the IP measurements will be presented to you under the status button for IP. Under the QX, you go down and hit the menu down here, you hit the Fabrics logo, it brings up all the different analyzers for you. And the analyzers, then you can put on screen and move them around, double click them, they'll change sizes. In the leader, you can go into the layout, change sizes, change what you see if you want to go into a multi-view or a single view and actually look at all this stuff. So the tag is a great troubleshooting tool from a looking at, do I have video or don't I have video? It's pretty much a go, no go. When you're actually looking at video, it doesn't have the measurements because the de-encapsulator does not pass the metrics over to us. So what you typically get is something that looks like that. When you're looking at that video, it starts blinking off the screen for you. Just remember that IP is just another I/O interface. We are looking at different things. As we looked at in the last session we did, the frame sync errors don't pass through switches. Only RTP errors pass through switches. So you really need to look at the RTP errors to see packet errors down. You need to know what your normal packet interval, what is the signature of your system, so you know what it looks like under normal conditions and what it looks like when it's sick. And then the 2110 for sender models is your eye and jitter looking at your transmitters. And it's still a divide and conquer network. And going through things, you need to know from a block diagram point of view what your network or how your network's laid out. And with that, Kristen will entertain a few questions.
Thank you so much, Steve. I do have just a few questions. One of them is, are there any typical values with formats like HD and 3G?
Not other than timing. The timing will be that 21 line and the 42 lines. I'm looking at timing, but just as eye and jitter is transmitter and network dependent, your packet intervals when you actually look at your network are going to be dependent on your network properties.
I mean, this is where tools like the Fabrics handheld are really useful, because if you've got a pair of them, you can set one device up as the sender, connected at one end of the network, and then connect your second device as a receiver and use them as a pair, because you know what you're transmitting.
Yep.
Then you can measure it at the other end. And as Steve said, you get a signature, you get what's that normal operation for your system. And then when it starts to deviate,
yep,
maybe because people are bolting extra devices onto the switch or whatever, you can start to see that. So, you know, that's where these tools are really useful.
What PTP reference generator or source are you using, and how does it lock to BB?
So I am using the Leader LT4610. The beautiful thing about it is GPS locked, and it generates black burst. So it is my source of black burst. It is my source of PTP. Since they both come off the same GPS, they are absolutely locked to each other since they're coming out of the same sync source.
And obviously the other advantage of that is that should you lose the GPS connection, because
Yes,
they're in the same device, they will stay locked together, and not that they'll drift hugely, but they will move together.
yes.
And that's another issue that you can see if you have separate devices with black and burst and PTP. You lose GPS and they deviate at different rates.
Yes.
So that when you transition from your IP world to your SDI world, you get an interruption to the picture quality.
Kevin and Steve, do you have anything else you want to say before we wrap this up?
No, I mean, as Steve said at the beginning here, if you've got questions, if you've got subjects concerning these IP and hybrid installations that people are starting to deploy, drop them to us. You know, it probably could make a presentation on its own. You know, there are lots of things going on out there, and you know, with the Leader and Fabrics tool sets, we've got the answers to the questions, and you know, we'd be more than happy to explain how they can be used.
Thank you again, gentlemen.
Thank you, everybody. Thank you, Kevin. Thank you, Kristen. And have
Thank
a
you.
great day, guys.
All the best.